Hello everyone, my name is Prabha. I am PhD student at IIT Bombay. I am also TA of this course. In the previous lectures, you have studied about the various type of hydrogen storage materials. For example, complex hydrides and the metal hydrides. In the metal hydrides also you have learned different type of metal hydrides that is being used for the hydrogen storage. For example, AB2 type of metal hydride, AB5 type of metal hydride. In the today's lecture, we have discussed about the design and development of metal hydride hydrogen storage. So, if we start with the metal hydride for hydrogen storage, we have to understand how the hydrogen is actually being stored in the metal hydride. Initially, the hydrogen molecule will adsorb on the metal hydride lattice, then the hydrogen molecule will dissociate into atoms. Then hydrogen atom, after dissociation of the hydrogen atom will occupy a lattice space inside the metal hydride lattice, and finally after occupying the lattice site, it will ultimately diffuse into metal and form metal hydride phase. It is also important to see the reaction of the metal hydride. When the metal hydride will react with the hydrogen, it will produce metal hydride, and the heat is also generated during this process. This is the process of absorption. After that, there are two processes that is being done for the metal hydride hydrogen storage. The first is the absorption, the second is the desorption process. The hydrogen during the absorption process, the hydrogen will supply to the metal hydride bed at a pressure that is higher than the equilibrium pressure of metal hydride. In the previous lectures, you have studied about the equilibrium pressures, which is a temperature dependent quantity. So, during the absorption process, when the hydrogen will supply to the metal hydride, it will absorb inside it. It is an exothermic process. So, the heat is being generated inside the metal hydride reactor. During the desorption process, when the absorbed we require this absorbed hydrogen, we will supply heat to it. After supplying heat, this hydrogen that is absorbed inside it will come out from the metal hydride reactor. For the desorption process, it is important that the equilibrium pressure of metal hydride needs to be higher than the outlet pressure. Now, the main driving force that I am talking about, the main driving force is the difference between the equilibrium pressure and the outlet pressure for the desorption process, and for the absorption process, the difference between the supply pressure and the equilibrium pressure is the main driving force. Now, we have seen from here that it is an exothermic process and it is an endothermic process. So, the heat that is being generated during absorption process need to be removed from the metal hydride reactor. In the desorption case, we need to supply this heat to metal hydride reactor. So, coming to the heat transfer issue in metal hydride. So, as I am saying that when the hydrogen is absorbed inside the metal hydride reactor, there will be generation of heat during absorption process. After absorption, it will increase the metal hydride reactor temperature inside the metal hydride reactor. This increment in the temperature will increase the equilibrium pressure. If the equilibrium pressure increases, the difference between the main driving force, that is the difference between supply pressure and the equilibrium pressure, will reduce and the reaction will stop. In the case of desorption process, when the desorption starts, there will be cooling effect during desorption, which will decrease the temperature of metal hydride reactor, which will decrease the equilibrium pressure. Again, the difference between the equilibrium pressure and the outlet pressure reduces and the reaction stops. So, during the absorption process, we have to remove heat from air to maintain the equilibrium pressure, and during the desorption pressure, we have to supply heat to maintain this equilibrium pressure, which will ultimately maintain the driving force and the reaction will continue. Now, we are supplying heat during desorption process, and we are actually removing heat during the absorption process. So, during this process, because the thermal conductivity of metal hydride lie in the range of 0.1 to 0.3 watt per meter Kelvin, this low thermal conductivity of metal hydride restrict the flow of heat inside the metal hydride reactor. So, this will put forward the requirement of efficient heat transfer requirement inside the metal hydride reactor, that is a prime requirement for the efficient transfer of heat inside the reactor. Coming to the basic design of metal hydride reactor, there are different parts of metal hydride reactor that need to be considered. The first is the hydrogen inlet. The hydrogen inlet will be supplied through a pipeline which is generally made up of SS316L material. Thus the hydrogen will then be absorbed inside the metal hydride reactor. During this process there will be a filter of hydrogen gas inside it. The filter is actually being used to separate the metal hydride from hydrogen during desorption process. When the hydrogen is absorbed inside the metal hydride, there will be expansion of metal hydride. So to compensate that expansion of metal hydride, we have to provide a expansion volume to the metal hydride reactor. Finally, there is a reactor wall. So the reactor wall is also be very important that need to be considered for the design of metal hydride reactor. So the first and the foremost requirement for the metal hydride reactor is it should be such that it will hold a high pressure during absorption up to a range of 50 or 60 bar or more than that, and during the desorption process it will also work into the vacuum pressure. Second important point for the consideration of reactor wall material is it should not be reactive to hydrogen and metal hydride. The third and the most important is the reactor material should be low in cost and it will be light in weight. So these are the requirement for the reactor materials. Coming to the next is we have to understand how much amount of hydrogen we need to store, and accordingly what is the volume of metal hydride reactor that we need to consider. So suppose we want to store x gram of hydrogen inside the metal hydride reactor, and we have choose a metal hydride which is having a gravimetric capacity of G%. It will be 1.4 or 1.58% for LaNi5. For Mg2ni it is generally lie in the range of 3.4 to 3.5%. So accordingly the gravimetric capacity will be selected. Now the amount of metal hydride required to store this hydrogen is calculated by this formula. Now we have the amount of metal hydride, we know the density of metal hydride, so the volume of metal hydride will be calculated by this formula. Okay. Now the next step is, because the metal hydride is a porous material, so there will be a porosity that need to be accompanied in the volume. So if the porosity of metal hydride is P and the expansion volume after absorbing hydrogen is around Z%, so the final volume of the metal hydride reactor will be calculated by this formula. After calculating the volume of metal hydride reactor, if we know the length and the diameter ratio or some other formulas other requirement of the metal hydride reactor, from there we will calculate the dimension of metal hydride reactor. Generally cylindrical shapes are used for the metal hydride reactor. Coming to the next slide is, we have to define the equation which will defining the process inside the metal hydride process during absorption and desorption. So first and the foremost is, when the hydrogen is absorbed inside the metal hydride reactor, there will be generation of heat inside it. So the temperature will change of the metal hydride will change accordingly. So the first equation which will define the change in temperature is the energy equation, which will define then the temperature with respect to time will change as the hydrogen is absorbed. So this term, the second term in the left side will denote the advection term, which is when the hydrogen will start flowing inside the metal hydride reactor, there will be some heat flow due to convection also. So this term will define that. The first term in the right side will define the conduction that is being happening inside the metal hydride reactor. K effective is the effective thermal conductivity of metal hydride, because when the hydrogen is absorbed inside the metal hydride, there are two materials now. The first is the gas, which is in the porosity of E, and the remaining portion of the porosity there will be metal hydride. So the effective thermal conductivity will be calculated by this formula. Now it is important to note that the velocity of hydrogen that is flowing inside the metal hydride reactor is very low. So generally when we are developing mathematical modeling or we are doing calculations, generally this term will be is not that much significant, but for the practical application we need to consider this term also. Now when the hydrogen is absorbed inside the metal hydride reactor, there will be change in density of metal hydride that will be given by the mass equation of bed. Finally when the amount of mass that is being absorbed inside the metal hydride reactor is calculated by this formula, and the mass of hydrogen dissolved is calculated by this formula. So, this amount of mass absorption and desorption will depend on the activation energy of material. So, it is actually depend on some of the material property. It will also depend on the other parameters also, like supply pressure, equilibrium pressure, and the density of material is also important. When this reaction will happen, there will be reaction constant of these also. So, these are to the reaction constant. In the previous lecture taken by Professor Pratibha Sharma, she will define that the equilibrium pressure will depend upon the enthalpy and the entropy of reaction. So, this is the formula for the equilibrium pressure that we calculate. Now, there is a heat capacity also, effective heat capacity, which will be calculated by this formula. Now, if we start to design the metal hydride reactor, the first and the foremost thing is that for what application this metal hydride reactor is being used. So, the most important thing of metal hydride is there is a wide range of temperature, and there are different type of metal hydride available in market which will work for a wide range of temperature. So, if we work for the main applications of metal hydride reactor is for heat pump, for vehicular application, for thermal storage systems, for refrigeration, for heat transformer also, for hydrogen transport it will be used, and for fuel cell integration also, for continuous supply of electricity. So, if we are able to define the application of metal hydride reactor, we are able to know the working temperature and the pressure range for particular application. After knowing the temperature and the pressure range, we will also need to define what is the amount of hydrogen that need to be stored inside the metal hydride reactor. From the working temperature and the pressure range, we are able to select the metal hydride. From the metal hydride, we will calculate the volume of metal hydride reactor from the amount of hydrogen to be stored. The volume of calculation will be done in the previous slides. After the calculation of the metal hydride reactor, we will find the optimum L by D ratio. In the literature, it is found that the generally optimum L by D ratio lie in the range of 3 to 4. From there, we will be able to calculate the length and the diameter of the metal hydride reactor if we are using a cylindrical metal hydride. After the selection of the metal hydride, we have to select the metal hydride reactor material. Suppose for vehicular application, we require a metal hydride reactor which is low in weight. So, for that we need to select aluminium as the metal hydride reactor. But for the stationary application, for example thermal storage, for refrigeration, we will select SS316L or other material accordingly. After selecting the material, we will find the thickness of reactor. It will depend on the pressure in which we are working. Suppose we are working in a pressure range of 30 to 40 bar, we have to choose a factor of safety which lie in the range between 2 to 3 generally. After selecting factor of safety, we will find out what is the maximum pressure that we have to design our system for. From there, from the ASME pressure vessel code, we are able to calculate the thickness of reactor. After calculating the thickness of reactor, now we are able to develop a cylindrical reactor up to now. Then the main problem is the heat transfer inside the metal hydride reactor. So, we have to provide some heat transfer arrangement inside the metal hydride reactor for the fast absorption and desorption. Then we optimize the parameter for the particular selected heat transfer arrangement. This will complete our design of metal hydride reactor. Then we will do the performance analysis of reactor. If it is good for our particular application, then we will go with that. Otherwise, we will follow the same step again. Now, it is important to know what are the main parameters which is affecting the metal hydride reactor performance. So, the first and the foremost is the supply pressure. So, the difference between the supply pressure and the equilibrium pressure, this is the case of absorption. When the difference in the supply pressure and the equilibrium pressure is the main driving force which will allow the hydrogen to get absorbed inside the metal hydride reactor. So, supply pressure need to be as high as possible accordingly. So, the driving force will be as high as possible. Second is the L by D ratio. It is also a very important parameter because when we increase the L by D ratio, the thickness of the bed will reduce, and this will reduce the conductive resistance inside the metal hydride bed, which will further increase the heat transfer inside metal hydride reactor. The other and the foremost property is the thermal conductivity. If we somehow able to increase the effective thermal conductivity of metal hydride, so this increment in metal thermal conductivity will allow us to have a greater faster heat transfer inside the metal hydride reactor. The other important portion is the heat transfer coefficient. Heat transfer coefficient, when the heat transfer coefficient, when we are cooling the metal hydride from the outer portion, and if the heat transfer coefficient is higher, there will be a faster removal of heat or faster supply of heat from the outer portion. So this parameter is also very important. The other important parameter is the external temperature. The difference between the outer temperature and the metal hydride reactor temperature need to be as high as possible, so that there will be a faster heat transfer. The other important parameter is the system cost. System cost is very important because it needs to be as low as possible for a particular application. Now there are different ways to improve the heat transfer in metal hydride reactor. So we have a heat equation which is generally defined by the conductive term of the heat transfer and the convective term of heat transfer. Okay. Now we want this heat transfer to be as fast as possible. So we have to look into these parameters. So if we initially look at the thermal conductivity of metal hydride. So this metal hydride thermal conductivity of metal hydride will be increased by introducing metal forms and ENG compacts, expanded natural graphite compact, so that it will increase the effective thermal conductivity. So the effective thermal conductivity formula that we already have, E1 K1 plus E2 K2 plus E3 K3 plus like, and E1 plus E2 plus E3 need to be equal to 1. So as we increase as we introduce number of thermal material inside this metal hydride reactor with higher thermal conductivity, so the effective thermal conductivity of metal hydride will increase, and this will increase the heat transfer inside the metal hydride reactor. This will be done by using metal forms and ENG compacts. The second important parameter is the decrement of delta X. Delta X is actually providing a conductive resistance to the heat transfer. So this need to be as low as possible. So this will be, we are actually achieving this by having the multitubular reactor. Suppose we have a reactor like this. So we will convert this reactor into a multitubular reactor having multiple tubes inside of metal hydride inside it. So with having a multiple tubes, so we will actually reduce the thickness of metal hydride bed, which will increase the heat transfer inside the metal hydride reactor. Another important parameter is the area of heat transfer. Generally, area of heat transfer will be improved by number of things. The first and the foremost is the using of fins. We can use fins inside metal hydride reactor. The second important is we have also provided the heat transfer fluid jackets. And the third is using the cooling tube. So these are the three things that we can use to increase the heat transfer area of metal hydride. So generally the different type of fins are being used. I will explain the next slide. Other important parameter is the difference of temperature difference. So the temperature difference is done by, suppose we have a metal hydride reactor and the temperature inside is Ts and the outlet temperature is T0. So the temperature, when we decrease this temperature for absorption, so this temperature difference will increase and this will result in higher heat transfer. Another important parameter is the heat transfer coefficient. So the heat transfer coefficient will be increased by using different type of heat transfer fluid and by increasing the velocity of heat transfer fluid inside the tubes or different type of tubes that we are using. So we will start with the increment in the thermal conductivity of metal hydride. So we have used metal form like this. So initially the thermal conductivity of metal hydride is 0.1 to 0.3 watt per meter Kelvin. Then we introduce a metal form having a higher thermal conductivity like aluminum form, copper form inside this metal hydride reactor. So it will increase the effective thermal conductivity which result in faster heat transfer. Similarly, the ENG compacts are also used. ENG compacts are first mixed with the metal hydride particles, then will be the ENG with the metal hydride will be compacted, and this compact metal hydride will be used with which is having a higher thermal conductivity. The main problem with these metal form and the ENG compact is they will occupy some volume inside the metal hydride reactor, and it increase the weight and the size of the reactor also. So if we are designing a metal hydride reactor, there must be a trade off between their effectiveness and dead weight, what they add to the reactor. Coming to the increase in the heat transfer surface area, there are different type of fins that will be used for the inside the metal hydride reactor or outside the metal hydride reactor. So this is a metal hydride reactor. At the outer periphery there is a fins that will be attached to the metal hydride reactor which will increase the heat transfer surface area. This is a longitudinal type of fins, this is a transverse type of fins that is being used. Ultimately fill will increase the heat transfer surface area which will result in faster heat transfer inside the metal hydride reactor, and finally there will be faster absorption and desorption. The main problem with the use of fin is it will increases the weight of system. So we have to, again there will be a trade off between the weight and the type of fins and the number of fins that we are using. The similar type of arrangement will also be used inside the metal hydride reactor to have a faster heat transfer. The other way to increase the heat transfer surface area is to introduce a water jacket at the outer periphery of metal hydride bed. So the main requirement is it will provide the necessary condition for heat transfer during absorption and desorption. It will increase the heat transfer surface area. The water that is being used inside the metal hydride, the temperature of that water is also a very important parameter that need to be considered. The main problem using a water jacket is it will provide heat transfer for the outer periphery, but at the core, in the core region, the transfer of heat will be difficult. So the transfer of heat in the core region is difficult for when we use water jacket. So this problem will be solved by using cooling tube. So the number of researchers using different type of cooling tube inside the metal hydride reactor. So the main advantage of using cooling tube is they will provide uniform heating and cooling. Different type of cooling tubes are used such as helical tube, U-shaped tube, straight tube with different arrangement like given in this figure, and then the main problem with these type of cooling tube is they will occupy some volume inside the metal hydride reactor which will increase the size of reactor. Similarly, there is another way to improve the heat transfer, to increase the heat transfer inside metal hydride reactor, which is by increment in the heat transfer coefficient. This can be done by increasing the velocity of heat transfer fluid, or we have used different type of heat transfer fluid also for the system. Suppose we are using air and water as a heat transfer fluid. So at the same velocity, water will provide a higher heat transfer coefficient as compared to air. Coming to the combination of methods, there are different type of combination that is being used, such as cooling tube along with the fins, along with the metal form, along with the water jacket. So there are 4 type of combination that is directly being used by different researchers. The advantage of this is this will provide a very fast absorption and desorption inside the metal hydride reactor due to faster cooling and heating. But the main problem is this will occupy a lot of space inside the metal hydride reactor and ultimately increases the weight of the system. This is up to the design of the system. Accordingly, there are different type of application of metal hydride reactors which will also decide what type of metal hydride we need to select, what is the shape of the metal hydride we require enhancement in thermal conductivity of or not. These are different things that will be defined by the application of metal hydride reactor. So suppose if we are using it for the refrigeration, so we have to look into the desorption process, not for the absorption, because during desorption process the temperature of metal hydride will decrease. So for refrigeration process we have to decide the desorption, we have to concentrate on the desorption thing. When the temperature of metal hydride reduced, the reduction in the temperature inside the metal hydride reactor will provide a higher temperature difference between the inner and the outer portion of metal hydride. So, if the inner metal hydride reactor is at lower temperature and the outside temperature is at higher temperature, so this will be extract heat from the space that need to be cooled, and this will produce a cooling effect at the outer portion. So, the material will be, the material that we need to select for refrigeration will be such that it will provide a cooling effect up in a particular temperature range that is required by particular application. The other application of metal hydride reactor is thermal energy storage. The main advantage of metal hydride is it will provide a very wide temperature range. So, energy storage of around 700 to 800 degree is also possible with metal hydride reactor. The metal hydride reactor thermal energy storage have higher energy density compared to other like phase change material and sensibility storage system. Long term storage is also possible in metal hydride reactor. The space requirement is also less compared to other energy storage system. The other application of metal hydride reactor is the fuel cell integration, in which the metal hydride reactor is incorporated with the fuel cell and the fuel to continuously get the electricity. So, the important thing is the metal hydride reactor when connected with the fuel cell is an auxiliary way to generate electricity. The most important thing is the output of fuel cell is water vapor. So, ultimately this process is a eco-friendly system. The main problem with this integration is the synchronization of hydrogen flow rate. When the hydrogen that is coming out from the metal hydride, we need to supply that hydrogen to fuel cell at a particular flow rate. So, this synchronization of hydrogen flow rate is very important in the fuel cell. That is one of the problem, and that is the research is going on in this field.
In the previous modules, we have learned about the different methods of hydrogen storage. At IIT Bombay, we are working on solid state hydrogen storage. We do work on different type of materials like chemical hydride, complex hydrides, metal hydrides, starting from DFT studies to look at the different materials, different alloys, the possible dopants which can improve onto the performance of these materials, to synthesizing these materials in small scale, and then after studying, doing a thorough characterization, studying their hydrogenation, dehydrogenation behavior, we synthesize materials on large scale. With these large scale materials being synthesized at IIT Bombay, we use these materials for different systems. Now, these hydrogen storage systems, this development requires simulation, then optimization of the reactor geometrical parameters, their performance parameters, and thereafter fabricating, integrating these for various applications. Now, in this particular module, we are going to learn about the different experiments, synthesis methods, characterization of these hydrogen storage materials as well as systems.
This is a wet chemistry setup has been shown here. We will be demonstrating the dehydrogenation of chemical hydride using water in presence of catalyst. Under stirring, the material has been added to the solution. Now the chamber is closed. Shortly we will see the hydrogen generation. Now you can observe that the hydrogen is accumulating in the burette by water displacement method. The instrument showing here is known as thermogravimetric analyzer, and it is coupled with mass spectrometry. In short, it is called TGA-MS. Now we will open the chamber. The crucible is filled with a certain amount of sample. Now the chamber is being closed and we will run the program. Here in the screen you can see we are running the programming, and the program has been started and it will take around 1 hour and 26 minutes. Upon completion of the experiment, these are the pattern we got. Now we will further analyze the reading that we got.
A laboratory glove box is a sealed container that allows safe handling of the materials or chemicals sensitive to atmospheric exposure under a controlled inert atmosphere. Certain hydrided alloys are pyrophoric in nature, meaning they are liable to ignite spontaneously on exposure with air. Loading and unloading of materials can be done through this anti-chamber. Weighing and loading of the sample into the sample holders can be done inside the glove box to isolate the sensitive materials from the outside environment, protect operators from hazardous materials inside the container, or both. The oxygen and moisture content of the glove box are monitored by the inbuilt sensors and are kept in check by using the purging technique. Depending on the size or volume of the material to load inside the glove box, there are two different sizes of antechamber present with this apparatus. Purging of the glove box is done with the help of vacuum pump. In order to maintain an inert atmosphere throughout, the glove box is supplied with argon gas from these cylinders on a continuous basis.
Based on loading capacity, ball milling can be industrial ball mill and laboratory ball mill. Laboratory ball mills can be planetary, rotary or vibratory type. Ball milling involves many parameters: milling time, milling speed, ball to powder weight ratio, ball and vial material type. Here we can see different types and sizes of vials and balls. This one is stainless steel, but it can also be made of tungsten carbide, zirconia, agate, etc. Depending on the hardness of the material, the ball and vial is chosen. This here is a high energy planetary type ball mill of freeze make. From this panel, milling time and speed can be set. The vial is attached through a clamp. Here in this we can see this vial is made of tungsten carbide. And we can also see that the base panel is so connected that the base plate moves clockwise, while the vial part can move anti-clockwise direction, which is showing that it is a planetary type. Generally, ball milling is used to synthesize equilibrium and non-equilibrium alloy phases, usually at room temperature, such as supersaturated solid solution, metastable crystalline phases, nanocrystalline phases, and even amorphous alloys. Alloy formation happens by mechanical action of repeated fracture and welding. So, this is the sample that was observed at 2 hours, this was observed at 5 hours, and this one is 10 hours. The evolution of structure can be confirmed from the XRD analysis, and finally, we can arrive which type of solid solution we require, and we can achieve that. Although ball milling is easy to use on laboratory scale, but the range of parameters is huge, which poses two challenges. Firstly, the comparison between studies from different types of ball milling machine is quite difficult. Secondly, the relationship between laboratory and industrial scale is not obvious, but optimization of milling parameters could give a direction to industrial apparatus.
In our lab, arc melting furnace is an instrument used for small scale synthesis of hydrogen storage alloys using different hydride forming elements. The composition or sample to be melted is kept in water cooled copper hearth. The heat required to melt metal is obtained via an electric arc established by contact between electrode, basically tungsten, and copper hearth. The energy required to form an alloy depends on its composition and quantity, which is achieved by varying current in this instrument. For a given sample, the repetitive melting of 3 to 4 times is performed to obtain homogeneous alloy. The arc melting furnace present in our lab is capable of synthesizing 25 grams of alloy in one batch.
Vacuum induction furnace is based on two main principles: mutual induction and heating effects of electric current. A primary coil working at high voltage induces eddy current in the metals inside the furnace, which produces heat due to the resistance in the metals and causing them to reach their melting point and form alloys and compounds. Here we have a customized induction furnace that can produce temperatures in the range of 850 degrees Celsius to 2000 degrees Celsius. The constituents from which our material is to be made are first loaded in these special graphite crucibles. Depending on the mass of the material to be made, which can be from 200 grams up to 10 kgs, we select a suitable crucible. This crucible is then placed in the furnace. In order to form the alloys and compounds, first a vacuum of about 10 power minus 6 millibar is produced inside the chamber using the rotary root and the diffusion pumps. Using the rotary root and diffusion pumps, then the high voltage supply induces current in these metals that is sufficient to produce enough heat that they reach their melting points. The molten metals mix into each other and form the desired material. The temperatures inside the crucible can be indirectly measured using the pyranometer attached to the chamber. The melt is then poured into copper mold to form ingots. The copper mold uses a flow of water typically maintained below 10 degrees Celsius for cooling these ingots. Here we have the chiller that produces the flow of cold water, which is then fed into the furnace by means of these pipes that we see here. The formed ingots are then removed from the copper mold and then used in the systems.
The capacity of hydrogen absorbed or desorbed in the alloy is measured by two techniques, gravimetric and volumetric. In our lab, we have three volumetric based homemade sievert apparatus ranging from low pressure systems to high pressures, that is up to 150 bar. A sievert apparatus generally has three inlet outlet connecting to supply of hydrogen, inert gas and to a vacuum pump. The high vacuum pressure can be achieved via rotary and diffusion pump up to 10 to power minus 6 millibar. The change in hydrogen pressure is measured using a pressure transducer. A pressure transducer is calibrated to convert pressure reading into electrical signal, which is further collected to a data logger. The pressure and temperature reading of each system can be seen on this panel, which is a programming interface of a data logger. To analyze the behavior of the alloy which were synthesized by arc melting or induction melting technique, then it is crushed into powder and placed into a sample holder as shown here. Depending on the nature of experiment to be performed on particular alloy, it can be loaded into the sample holder either in the glove box or in the open surroundings. The sample holder is then positioned at one end of the apparatus, enabling us to provide heat treatment to the alloy. To perform experiment at high temperature, we use a portable heater that can go up to 1000 degrees Celsius. For experiments, hydrogen is filled into a standard reactor of known volume and pressure and released to a reactor site by opening these valves. The drop in pressure is then calculated for the hydrogen capacity of the alloy. This increase in temperature show exothermic reaction of the metal hydride. These apparatus can be used for absorption and desorption kinetic, pressure composition isotherm and cyclicity of the alloys.
Now, after you have seen manual civets apparatus, this instrument in our lab is a fully automated volumetric sorption analyzer of Haydn isochema make. This instrument works on volumetric measurement principle wherein for a given known dosing and sample volume, the drop in hydrogen gas pressure is correlated with the amount of hydrogen absorbed or desorbed by an alloy. Few grams of synthesized sample is loaded in sample cell which is attached here to the instrument and following experiments can be performed. Picnometry for determining the density of an alloy, rate kinetics for determining the rate of hydrogen absorption and desorption from an alloy, pressure composition temperature PCT measurement for determining the equilibrium pressure of alloy at different temperatures, analyzing the hysteresis, maximum as well as reversible gravimetric capacity and change in enthalpy and entropy of hydride formation. This instrument is also capable of performing cyclic life study of an alloy for 100 to 1000 cycles. The instrument in our lab can achieve a vacuum pressure up to 10 to the power minus 8 millibar using turbomolecular pump, dosing pressure up to 200 bar and sample temperature can be varied from room temperature to 500 degrees Celsius.
After synthesis of materials using ball milling, arc melting and induction melting, we will fabricate metal hydride reactor. In our lab, Before fabricating and integrating a system according to their end use, we will try to investigate the behavior of our metal hydride reactor by designing them mathematically using simulation software like COMSOL, NCERT and MATLAB. During these simulation, effect of various parameters are depicted on hydrogen absorption and desorption. Besides this, we also use various optimization technique using machine learning to optimize this system. This simulation and optimization technique helps in saving time, resources and cost for our lab. The optimized system is then fabricated scaling from 1 kg of metal hydride to 50 kg, incorporating various heat transfer arrangement like embedded cooling tube metal hydride reactor, hexagonal fin type of metal hydride reactor, embedded tube type of metal hydride reactor with different scaling sizes of metal hydride, the modular type of metal hydride reactor according to their various application like heat pump, heat transformer, thermal energy storage, etc. The reactor shown here is modular type of metal hydride reactor used for power backup. Now as you can see, we are dissolving hydrogen from this modular type of metal hydride reactor using sievert apparatus having mass flow meter that is recording mass flow rate and total mass of hydrogen dissolved using data logger. The temperature inside the metal hydride reactor and the temperature of the water bath are also recorded using a data logger. After heating the metal hydride reactor by the heat transfer fluid, the hydrogen that is being dissolved from this metal hydride reactor is flow through that through the sievert apparatus, and then this hydrogen will flow to the fuel cell. The hydrogen dissolved from metal hydride reactor is utilized by fuel cell, wherein it converts the chemical energy of hydrogen into electrical energy, powering a DC load. The parameter such as voltage, current and power is recorded in energy meter. This completes the integration of metal hydride reactor with real-time applications.